So, good morning, students. So, today we would like to discuss about some weak interactions, and it is generally known as Vander Waals interactions. And within this Vander Waals interaction, we will discuss about the dipole-dipole interaction force, dipole-induced dipole interaction force, and instantaneous dipole interaction force, and which is basically known as London dispersive forces. So, we know that most of the real gases condense to liquid phase at very low temperature, and when the pressure becomes very high. Okay, so it suggests that there must be some kind of attractive force operating between the gas molecules, and these intermolecular attractive forces are called the van der Waals forces. So interatomic attraction forces means that operating between two different molecules. Okay, and intra-atomic attraction forces means the force that holds the different atoms in the molecules, which is basically the covalent bonds. So intramolecular attraction force in a molecule, in a gas molecule particularly, I can say, is very stronger because it is a real bonds, and covalent bond is much stronger than these intermolecular attraction forces. So intermolecular attraction forces are not as strong as intramolecular attraction forces that I already discussed. For gaseous molecule, these intermolecular forces are not so important because gas molecules are far apart from each other. So it's very difficult to operating this type of intermolecular attraction forces between these two atoms, between these two molecules, as they are far apart from each other. However, intermolecular attraction forces are important for liquid and solids where the molecules are very close to each other, because that means when the molecules come very close to each other, then this interatomic attraction forces or intermolecular attraction forces is very important, and you have to take into consideration this type of forces. Okay. So van der Waals forces are of basically three types. The first one is the dipole-dipole interaction forces, dipole-induced dipole interaction forces, and the third one is instantaneous dipole interaction forces, and which are in commonly known as the London forces. Okay, so first, one by one, we will discuss about this thing. So first, we would like to discuss about the first point, that is dipole-dipole attraction forces. What does it mean? In the name, it signifies what does it mean. Dipole-dipole interaction forces means we know what is dipole. When the charge is separated between some distance, between some charge distance, then we can show that it's a dipole. Means it has two poles. When we just put these two dipoles in a collection of dipoles, then what they can do, they can attract the opposite dipole of the other molecules. Okay, so this type of attraction forces are generally known as dipole-dipole attraction forces. So this type of forces occurs in molecular solids of the polar molecules, because we know that to need the dipole-dipole interaction forces, you need some dipoles, and dipoles are not generally originated in a non-polar or totally homonuclear diatomic molecules. So for this to generate, means for this dipole to originate in a molecules, you have some uh, charge separation or electronegativity separation. That means you need some molecules which are basically polar. It has some pole, just like HCl, water, ammonia. And what is the basic thing of that? Because all these molecules contains one atom of a particular electronegativity, and the other atom electronegativity is not exactly same. They are different, and because of this electronegativity difference, you have some dipole separation within this bond. So taking the example of HCl molecule, as the electronegativity of the chlorine is in chlorine electronegativity is 2.8 is greater than the electronegativity of the hydrogen, and hydrogen electronegativity is 2.1 only. The bond in HCl is polar, because I have seen the bond here, HCl. So because of this attraction, the bonding electron cloud is attracted more towards the chlorine, and so it becomes partially negative charge. Del negative is shown here, and the hydrogen, because electron density is shifted towards the chlorine atom, so hydrogen becomes partially positive charge. So in within this molecule, you can say that a dipole is generated. So the orientation of the dipole is towards the chlorine atom. In liquid and solid state, molecules are touching each other. That means they are they are very situated in a place where they can touch either, that means within very close distance they are placing. At that condition, the positive end of the dipole attracts the negative end of the dipole of a second molecule as shown in the figure. That means if you place this type of molecules, means you set of polar molecules in a solid state or in the liquid state, then what happened? The dipole means positive negative, negative positive. It can attract the second dipole in this fashion. Means positive end is attracted by this fashion and negative end is attracted by this way, or it can attract it in this fashion, means a positive end of a one molecule or dipole attracts the negative end of a second dipole in this way, and this molecular positive dipole also attracts the second molecule negative dipole in the same way. So this will continue up to the entire molecular system. It is important to note that as the charges on the hydrogen and chlorine is partial, partial charge only, that means the dipoles which whatever we observe here is not a very strong or attractive forces, but because of the partial charge separation, these attraction force are only partial. Okay, therefore the dipole-dipole attraction between the hydrogen and chlorine molecules in HCl is not necessary not nearly as strong as the interaction between the Na plus and Cl minus ion in the NaCl crystal. What is happening in the NaCl crystal? We know that when NaCl crystal is formed, so Na plus ions and Cl minus ions come close to each other, and at a particular distance their attraction force becomes enormously high and they can form the lattice and the crystal. Okay, but in the HCl we know that HCl is at normal temperature vapor state, means if you open the bottle it will vaporize within few minutes or few hours. That means the attraction force are not so strong that it will become solid, but it can condense to a liquid phase at high pressure and low temperature. That means there must be some attraction force, and this attraction force is the partial charge, and this attraction force are originated because of this partial charge separation between the H and Cl. Okay, and these force are not strong as in case of the NaCl or any other ionic crystal type, because this is the total charge separation. This is not the partial charge separation. This is the this type of force is operating between the two permanent cations and anions. Okay, that is why HCl is a gas under ordinary condition, whereas NaCl is a solid at solid with high melting point. The greater the dipole moment of the molecule, the greater is the force of attraction. Means as the dipole becomes stronger in the molecule, the attraction force obviously becomes stronger, and your molecule becomes liquid to solid in this way. The effect was studied first time in 1912 by Kisum and is referred to as the orientation effect. So this effect is basically known as orientation effect. So another name of the dipole-dipole attraction force is orientation effect. The second van der Waals type force that we would like to discuss is the dipole-induced dipole forces. The name itself indicates what exactly means. One is the permanent dipole and other is the induced dipole. That means it will form because of the presence of this permanent dipole. So let's come to the point again. When a non-polar molecules means just like homonuclear diatomic molecules, where there is no separation of electronegativity, or there is no difference in electronegativity between the two atoms. Okay, just like oxygen, nitrogen, hydrogen, etc., comes in contact with a polar molecule or ions, an induced dipole appears on these non-polar molecules. That means when a non-polar molecule comes in contact or comes very closer to a polar molecule, then what happened? The polar molecule induce some dipole on the non-polar molecule, and because of these so formed dipoles in the non-polar molecule, the polar molecules attracts at that time the so formed dipoles of this non-polar molecule, and there is some attraction force operating, and this type of force is basically we name in this heading that dipole induced dipole attraction forces. The force existing between the dipole induced dipoles are called dipole induced dipole attraction forces or dipole induced dipole forces. This can be easily understood by taking the example of the solubility of oxygen in water. The electron cloud of oxygen in the gaseous state is symmetrically distributed around the two oxygen atoms, just like here we just give a demonstration of the how electron clouds can be distributed between between the bonding between the two oxygen atoms or around the oxygen molecules, you can say. And when the water molecule comes closer to the oxygen molecules, the oxygen is partially negative charge and hydrogens are partially positive charge in the water molecules. Then what happen if this oxygen atom approach these oxygen molecules, then because of this is also negatively charged, so it will repel the electron cloud, and the electron cloud is shifted from this oxygen atom towards the rear end. That means at the end there is a slight low in density of electron cloud, and at this end there is a slightly more density of electron cloud. And because of this distribution of the electron cloud around the oxygen molecules in presence of water, here delta positive charge is originated and delta negative charge is originated at the rear end. Okay, so as the negative end of the polar water molecule approaches the oxygen electron cloud gets distorted. At the near end a partial positive charge, that is here, and at the rear end a partial negative charge, that is delta negative, is generated, and the result is that water and oxygen molecules are now attracted to each other. Okay, so this type of interaction was studied first time by Debye in 1920 and are popularly named as induction effect. That means it is not initially present within these molecules, but in presence of a polar molecule this force is originated, that is induced. The polar molecule induced a dipole within a so-called non-polar molecule, and after that they attract each other, and this type of force is known as induction effect also. The third type of van der Waals forces that we would like to discuss is the instantaneous induced dipole interaction forces, or it's generally known as London forces. Okay, the attraction force that exists between a non-polar molecules are called London force or dispersion force, because these forces are originated within a molecule which is basically non-polar. That means how a non-polar molecule can attract each other, that is very interesting, because previously we have discussed about attraction between polar molecules, that is obvious, it can be understood easily. And in the second section we have discussed about a polar and a non-polar molecule, that is also understandable because it generates some induced dipoles. But what about this non-polar? Both are totally non-polar. How can this attract each other? So let's see. The attraction force that exists between two non-polar molecules are called London force or dispersion forces. To understand how non-polar molecules can attract each other, it is important to note that electrons in atoms or molecules are in a state of constant motion. We know that electrons and electrons cloud in a molecular atoms are in a continuous motion, and that means electron clouds are not in a static condition. On an average, their electron clouds are spherically symmetrical. So without the effect of any external electric field or any external perturbation or disturbance, we can say that the electron cloud is spherically symmetrical or symmetrical, not only spherically. Okay, when two nonpolar atoms or molecules approach each other, however, the attraction and the repulsion between their electrons and nucleus can lead to distortion in their electron clouds. And when this type of two nonpolar molecules, basically which electron cloud is spherically symmetrical, and when they are approach each other, then the nucleus of the first atoms or molecules can attract the electron cloud of the second. At the same time, the electron cloud of the first repel the electron cloud of the second. So both attraction and repulsion force working when they are come in contact or come in close to each other, and because of this attraction and repulsion force, the electron clouds become distorted and some instantaneous dipole can generate. Distortion in the electron cloud, that means dipole can be generated momentarily, means when they are come in contact, then only this dipole originated, and when they are moved from each other, then also this dipole have gone. That's why momentary. In the neighboring atoms or molecules, which leads to intermolecular attraction. Thus, London force are the attraction between the molecules that results from the temporary dipoles caused by the movement of electron. That means London force originated from the temporary dipole, means it just just originated when the molecules come in contact, and then when they move back or move from far away from each other, then this force have gone. So now we can give with a very beautiful example of helium and xenon atoms. Both are, we know that the noble gas. Okay, so two electrons. So first we will discuss about the helium atom. The two electrons in helium 1s orbital of helium atom is strongly attracted by the nucleus because of the small size of the helium atom, and electron cloud distribution is symmetrical because two electrons repel each other. What does it exactly means? Because we know that the two electrons in helium atom are situated in 1s orbital. So 1s orbital, we know that very close to nucleus, so both the electrons are strongly attracted by the nucleus. So that's why the electron cloud is strongly attracted, and at the same time both the electrons are caged in a very small volume of 1s orbital. So when they are come in contact, then one electron can be repelled by the other electron. That means because of this repulsion, their charge distribution or electron cloud distribution is spherically symmetrical. Okay, now the second point, that is however the size of the xenon much larger than helium. We know that having 54 electrons, and here is the electronic configuration: krypton, that is 36, 4d10, 5s2, 5p6 in the fifth orbital. That means the outermost electrons are present in the fifth orbitals. So attraction between the nucleus and the outermost electrons is much less than helium atom. In case of helium, it was in 1s orbital, which is very close, means just first orbital, so it's strongly attracted. But in case of xenon, the outermost electrons are present in the fifth cell, and the attraction between the nucleus and the fifth cell is much less. Okay, and because of the larger size of the fifth cell, the outer electrons have sufficient room to move away without getting too close to each other. What does it exactly means? When the electron moves in the fifth orbitals, then one electron can move without come into the influence of the other electron, because they have a much space. So the repulsion force that attracted between the electrons are also much less. The temporary dipoles of xenon is much stronger, fifth cell, okay, much without getting too close to each other. So because of this, so when two xenon atoms come in contact or come very close to each other, then one xenon atom can easily do some attraction and repulsion forces. And because of this attraction and repulsion forces, there originated some dipoles within this second xenon molecules. Okay, so the deformation of the electron cloud of the xenon atom is very easy, and because of this easy deformation of the electron cloud, they are originating some dipoles, and this dipole can attract each other. Okay, so the temporary dipole of xenon atom is much stronger, as it is easily polarizable than the helium case. We have already discussed this thing. Thus, xenon must be cooled to liquid xenon at atmospheric pressure. When the temperature, you have to cool down the temperature to 166.1 Kelvin, that is basically minus 107.1 degrees centigrade. In comparison to, if you would like to make helium to liquid helium at the same atmospheric pressure, the temperature should have to be reached at 4.3 Kelvin, which is very close to zero. That means minus 268.9 degrees centigrade. And from these two values, you can understand how the induced dipole plays an important role when the molecular weight or the size of the atoms or molecules becomes bigger. Okay, thus greater the number of electrons and further the outer electrons are far away from the nucleus, the more polarizable is the outer electron, and because of this more polarization, higher is the temperature at which the gas can be condensed to a liquid. Because we have discussed in the starting of this section that a real gas or even an ideal gas can be liquidified at when the pressure becomes very high and the temperature becomes very low. So at the same times, we can tell that we can't change both at the same time, so keep the pressures fixed at 1 atmosphere and then applying the lowering the temperature successively. Then we can see that xenon can be liquidified at only 166.1 Kelvin, but whereas if you like to liquefy helium to liquid helium, then we have to reach at 4.3 Kelvin. That means the attraction force that holds the xenon atom within the gas is very high in comparison to helium. Thus, greater the number of electrons and further the outer electrons are far away from each other from the nucleus, the more polarizable is the outer electron and higher is the temperature at which a gas can be condensed to a liquid. Thus, at the same time, I can give another example. If we look at the group 7 in periodic table, from fluorine to chlorine to bromine to iodine, in the last two cases, bromine and iodine, we can say that bromine is a liquid whereas iodine is a gas, and we know that iodine have much larger size and a higher number of electrons. That means its molecular weight is increases. So it is now clear, thus iodine is a solid and bromine is a liquid. It is now clear that the increase in the atomic number, and atomic number means number of electron also increases. That is, with the increase in the number of electrons, there is an increase in the melting and boiling point, and which follows to the London forces. So these are the total three forces, that means dipole dipole, dipole induced dipole, and induced dipole attraction forces. And these three type of forces discussed above are collectively known as Van der Waals forces. In all these interactions, the attraction potential energy varies as the inverse sixth power of the distance between the molecules, and it is generally expressed as the attraction force E, Van der Waals type, equal to minus k by r to the power 6. So k is a proportionality constant and the negative sign is used for the attraction. So these are the total forces, means on an average these three are the Van der Waals forces that we have discussed. Okay.